So this is the molecular modeling lab. And in this lab, we're going to get to play with these plastic models, but for making and drawing good Lewis structures for the many compounds that we're going to assess. You will definitely need a periodic table. So the first one is water, H2O. When I write TVE, that means total valence for oxygen and a couple of hydrogen atoms. So think about number of neutral hydrogen. So 6 for oxygen plus 2 for each of the 2 hydrogens. Now, the atom that there's one of in this structure is oxygen. That's going to be the oxygen, each of 2 satellite hydrogens. And in order to make that connection, if every bond is a pair of electrons, that uses up 4 of the total 8 valence electrons, which gives us 4 of those electrons left over around the central atom to satisfy the octet rule, and hydrogen. Don't worry about it, seriously. So this is actually a beautiful Lewis structure, ox 7, 8 electrons, and each of the 2 hydrogens have access to the 2 electrons that are in that single bond. The electron groups around the central atom, single bonds count as an electron group, but so do lone pairs of electrons. Electron groups around the central atom, which makes it tetrahedral geometry, like 2 are lone pairs. So lone pair number 1, lone pair number 2. And then to figure out molecular chart that's at the top of the lab. And in that chart, it lists, okay, if there are 4 electron groups, there's the name of the shape is bent. It sounds non-scientific, but it actually is the scientific name for the molecule. It's to be done for each of these compounds prior to building it and making sense out of the build. Okay, next one, NF3. In that compound, a single nitrogen atom, which is column 15, and 3 fluorine atoms, each of which math. 3 times 7 is 21, plus another 5, that's 26. Connect that molecule so that the central atom directly connects. And to make that connection at a minimum, you need 3 single bonds. So of the 26, we've used up, that gives us 20 valence electrons left over. And we've got to satisfy octet rule. Happy to soak up 6, because if they're connected to a single bond to begin with, then another 6 around each fluorine gives it 8 electrons we've got to find a home for. The other 2 are happy to go on that central nitrogen. These single bonds, you've got a pair of electrons that it has access to, plus another 2 in the lone pair around it. So it follows octet with this. Each single bond counts as 1. 1, 2, 3, and then the lone pair makes in the central atom. We've got tetrahedral electron geometry. Of those 4 electron groups around bonding or lone pair, so we'll write that as 1. And we will refer to our handy-dandy chart at the top of the lab. One lone pair. We've got trigonal pyramidal molecular shape. Next one, rapid fire here. OI2. Oxygen, column 6 down in group 17. So 2 atoms that each contribute 7 valence electrons. 13 plus 6 from the oxygen gives us 20 total valence electrons. Fluorine, or 2 iodine, sorry. So that central oxygen needs to connect directly 2 single bonds, which consumes 4 of our total valence electrons, giving 16 left over by octet rule. We can take 6 dots around each iodine. That takes up central oxygen. Now, if you count up electrons around each atom within the structure, the iodine on either side, 2, 3, 4, 5, 6, 7, 8. So we're good on octet rule. If you're satisfied with that Lewis structure, then we count total as 1, so the lone pairs. So that gives us, once again, 4 electron groups around the central atom, and tetrahedral. Okay. This is looking a lot like water, right? Water has 4 electron groups and 2 lone pairs, or 2 lone pairs and 4 electron groups around the central atom, gives us a bent molecular shape. CH4 is the column that has 4 valence electrons for carbon, and then 1 for each of the 4 1 plus 1, 8 total valence electrons. And if carbon is the central atom, because there's only 1 of them, and we're going to attach it directly to each of the 4 satellite hydrogen atoms, and there's a pretty high number of bonds, it still is going to work out. So 4 single bonds would no electrons left over in this one. But doing an octet assessment for that central carbon, 2 will follow. And for each hydrogen, each one is happy with access to just the 2. So we are A-OK, all good. Hang on one sec. Oh, thank you. Melly, okay. Melly, come on now. All good. Okay, so if we count electron 2, 3, 4, the central atom, each single bond around the central atom counts as 1. Electron geometry. This time there are no lone pairs, absolutely none. So on our chart, we have the molecular shape matches that of the electron geometry. We have tetrahedral tetrahedral molecular shape. So far, so good. Next, we've got NH3. Once again, we start by referring to the periodic table. So nitrogen valence electrons, and then 1 for each of the hydrogens. So 5 plus 1 plus 1 plus 1. That gives us 8 bond work. We need a direct connection between the central nitrogen and each of the 3 hydrogens. That requires 3 electrons, leaving 2 left over. Those 2 leftover electrons need to go on that. So the central nitrogen has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. Connected by a single bond to the central atom, it's satisfied. We're all good on that. Okay, let's count electron groups around the central atom. Counts as 1, giving us 4 electron groups, and therefore tetrahedral geometry. Of the 4 electron groups, the CH4, none of them were lone pairs. This time we've got 1 lone pair with tetrahedral geometry. Electrons, we still have trigonal, pyramidal, molecular shape. CF4. Again, we start by referring to the periodic table. We'll look at 14 fluorines in column 17. So mentally, we're thinking, okay, 7 electrons for each fluorine. So that's 28 plus 4, 32 total valence electrons. Fluorines, that uses up 8 of the total valence electrons. We need 24 left over. And we have to satisfy octet rule for the fluorines. 4 of them, well, that's 24. 6 times 4 is 24. So the carbon's happy, and then the fluorines are happy because they have access to their own 6 electrons plus another 2 from the bond. That gives us tetrahedral electron geo, and there are no lone pairs. So this one's kind of like CH4, but it's, if you look at your molecular shape chart, if you have tetrahedral geo and no lone pairs, the name of the molecular shape match. Okay, here's an interesting one. CH2I2. Don't freak out because there's so iodine is in the halogen column, 7 valence electrons each. Carbon's in the carbon column, column 1, 1 electron each. So 4 plus 1, that's 6, plus another 4 electrons. The atom that you only have one of, the carbon, that's your central atom. We'll make, and each of the other atoms. Okay, that connection took 4 single bonds that consumes 8 valence electrons. We have 12 left over, hydrogen to the central atom, but iodine needs more electrons. If you put 6 around each of the 2 iodines, that's a good structure. Okay, just like the previous couple, we're 4. And once again, it's tetrahedral GO with no lone pairs. And in that case, the molecular shape. Okay, now up until now, we've compounds, we're going to have a chance to actually break the octet rule. Take a look at SF6. The very fact that we're going to need, at a minimum, 6 single bonds, which means that takes 12 electrons. And that means on your periodic table, sulfur, column 16, right below oxygen, group 17, so 7 valence electrons. Let's do a little math together. 6 fluorine at 42, plus 6 from the sulfur, so 42 plus 6 electrons. At a minimum, we need to connect a central sulfur to each of 6. We're exceeding the octet rule. And you might say, hey, can this compound even? And in fact, there are certain circumstances under which the octet rule is eligible to be violated. And if you maybe recall from class notes, it's the central atom, number 1. And number 2, if that central atom is in period 3 or somewhere else below period 3 on the periodic table. Sulfur is in the 6 fluorines to that central sulfur. It consumes 12 valence electrons, 36 valence electrons that we can place around those fluorines. The fluorines are not the central atom, so they must follow octet. And furthermore, so it wouldn't be eligible to violate octet anyway. Let's place 6 dots around each of math there, 6 times 6. That uses up 36, all 36 electrons, and each fluorine has access to exactly 8 electrons. The central sulfur has access to 12 electrons. Each single bond counts as 1. So 1, 2, 3, 4, 5, 6 electron groups around the central atom. Geometry. Of those 6 electron groups around the central atom, none of them are lone pairs. Is very helpful. 6 electron groups, so looking at the bottom row of the chart with no lone pairs. The name of the molecular shape, octahedral molecule. Okay, a few more. We're off to the races here, kind of rapid fire. Doing great. EF5, the octet rule. If you find phosphorus, it's right below nitrogen on the periodic table. And then F is in column 17, the halogen column, which each atom in that column contributes 5 atoms, each of which contribute 7 valence electrons. That's 35, plus another 5, not 14, 40 total valence electrons. Okay, directly to each of the 5 satellite fluorine atoms. And in doing that, electrons, which gives us 30 electrons left over to place around the fluorines. The central, just by being connected to 5 other things. That's okay because, number 1, phosphorus is the central atom. And number 2, phosphorus table, so that's okay. Each fluorine should receive 6 dots in order to find follow the octet rule on each of 5 satellite fluorine atoms. That accounts for all 30 of the leftover electrons. So this is a good Lewis structure. Okay, doing great. Let's tackle the last 5. And we'll begin by referring to the periodic table, as we always do. Fostering 5 valence electrons. Fluorine is found in the halogen column, which has 7 valence atoms, each of which carry 7 valence electrons. That's 35, plus another 5 from the phosphorus. We connect that central phosphorus to each of the 5 satellite fluorine atoms and electrons around the central atom. Now that's okay because phosphorus is the central atom, number 1, and it's in the 3rd period. The connection to the 5 satellite fluorines, that used up 10 valence electrons, which gives us 30 left over. Each of the fluorines giving 6 to each one so that they follow the octet rule. Satellite fluorines has spoken for all 30 of the leftover electrons. Now, 2, 3, 4, 5. And if you remember the name of the molecule or the types of molecule, trigonal bipyramidal electron geometry. And of those 5 electron groups around the central atom, none of them are lone pairs, that of the electron geometry, also trigonal bipyramidal. Okay, now we'll get to the multiple bonding situations. These are the really interesting ones. O2 is found in column 16. And so each of the 2 oxygen atoms carries 6. So we've got 12 total valence electrons. Whenever you have to be connected to each other, so there's at least a single bond connecting the 2 atoms. All right, valence electrons giving us 10 left over. Now, we need to get creative here, students, because oxygen is not in period 3 or somewhere else below that on the periodic table. It's in period 2. As it turns out, a deficit of electrons. Like if I take these 10 valence electrons left over and maybe put 5 around each of the oxygens, they each have access to 7 valence electrons. So that's not enough. When we violated the octet rule, not by having fewer than 8 electrons. So we need to increase electron ownership. And one way to do the left side shares one of its electrons. And simultaneously, let's say, shares one of its electrons. Upon doing that, let's redraw this. We now have each oxygen atom with its own, an electron belonging exclusively to the oxygen on the left side is now shared. And what was once an electron belonging entirely to the oxygen. Count the number of electrons that each oxygen atom has access to. 1, 2, 3, 4, 5. So it's a symmetrical molecule. It'll be the same for the oxygen on the right, but let's count anyway. 1, 2, 3, 4, 5, 6, 7, 8. We have either no central atom, or there's only between 2 atoms. It's linear electron geometry. The linear geometry is what it's make up a line in math class. There's no central atom, so I'm going to strike this question. It's not relevant. Their shape, therefore, if you take a look at our chart, there's only one option with linear electron, but we've got a good structure here. Okay, N2. Each nitrogen atom contributes in column 15. So 2 atoms which each contribute 5 valence electrons gives us a total of these. So this one there's going to be quite a bit of trial and error. Single bond between each of 2 nitrogen atoms. That would take up 2 of the total valence electrons, leaving us 8. 4 electrons around each of the nitrogen atoms. Now, nitrogen, kind of like oxygen, is not period 3 or some lower period. So we need to increase electron ownership until we get at present. We've got 1, 2, 3, 4, 5, 6 from the bond. And then same thing for the oxygen or the nitrogen. Single electron, like we did with the oxygen, we shared 1 electron. Let's try electrons for each of the 2 nitrogen atoms. So this time we've got, upon trying to into bond contributed by the nitrogen on the left side, and another brand new bond contributed by the nitrogen on the right side. We count up electron ownership. We've got, for the nitrogen on the left side, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Awesome. They each follow the octet rule. And kind of like what we did, whenever you have just 2 atoms, we've got linear electron geometry. We don't need to consider groups around this. No lone pairs. So necessarily, if we're talking linear electron geometry, the only that down as well. Okay, last one, CO2. Referring back to the periodic, and each of 2 oxygens contributes 6. So 6 plus 6 plus another 4 times. And if we start by attempting a connection of single bonds of each oxygen to the central carbon, that 12 valence electrons to place around the atoms within the structure. Eligible to violate octet rule because, hey, it's in period 2, both carbon and oxygen. So we need to get first, well, I'm going to make sure that the oxygens follow octet rule. Maybe put 6 around each of them. But then that needs access to 8, and it currently only has access to 4. We need to increase electron ownership. Let's have each of the satellite oxygens contribute an entire pair of electrons. Then let's draw this over here. We have a double bond on each side of the central and new as contributed by each of the 2 oxygen atoms. Each of the 2 oxygens also donate the lone pairs or they donated one of the 3 lone pairs they originally had in that first structure. The oxygen on the left side, it has access to 1, 2, 3, 4, 5, 6, 7, 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And lastly, let's consider the carbon. 1, 2, 3, 4, 5. Interestingly, this molecule can be drawn validly another way. It's not the way that I showed you, bond, single bond. So this is a valid Lewis structure as far as we're concerned. In this course, there's something called formal charge that makes this structure. So for our purposes, this is your structure. And we have a center around either side of it. Any type of bond, whether single or double or triple, all counts as 1 electron group. It's linear electron geometry. None of the 2, or neither, I should say, neither of the 2 electron groups are lone pairs. Symbol with linear electron geometry is a linear molecular shape. Okay, so now that was the hard part of this lab, to build all of these molecules out of our plastic models. And that's so now for the fun part of the molecular modeling lab. We've done the work of writing the Lewis structure, identifying electron geometry, and the molecular shape. Now we get to play with the plastic modeling kits. Now I'm just going to tilt this down for a sec and show you the pieces. So we've got several different colors of plastic balls and connectors, and those plastic balls have holes drilled into them that are appropriate for the bonding angles for the atoms that they represent when they're properly bonded. So let's review what we had said for the first compound, which was water, H2O. We had said that its molecular shape is bent. Typically, in a molecular modeling kit, the red balls represent oxygen. So what I'm going to do is insert into the 2 holes, and there are only 2 holes in the oxygen atom, 2 short connectors. And then I'm going to connect on the ends of those two white balls, which are typically representing hydrogen. Now, what would you say, how would you describe the shape of this molecule? Well, students, look, it is a bent shape. It's like almost like a V or a boomerang. And that's why water, if you're just looking at the bonds, has a bent shape. Now, keep in mind, there are two lone pairs of electrons, one over here, that are not shown in the bonding angles. But the angle here is roughly 109.5, but there is something called bond angle distortion, which is not a topic that we're going to get into, but it's a little bit less than 109.5, typical of tetrahedral geometry. Okay, next one, OI2. So once again, we have oxygen as our central atom. And in our modeling kits, I'm inviting students to consider either the green balls, or in our particular case, we've got orange balls to represent halogen atoms. So iodine, OI2, that's one oxygen and two iodines. And just like water, we have a bent shape. So same shape as before, lone pairs of electrons up top, and that's why we call this bent. So you can see why this is the fun part, right? Okay, molecule 3, NF3. We're going to use the light blue ball to represent the central nitrogen, and I'm going to insert 3 connectors. And once again, we're going to let the orange represent halogens. So iodine was a halogen, but so is the fluorine in NF3. Now take a look at this molecule. We've got, you might say, oh, it kind of looks like triangular, but if you look at it a little bit differently, these 3 orange balls, if I were to set them flat, are in a different plane than the nitrogen atom. The nitrogen's up above. And if you take a look at the Lewis structure for NF3, there's a lone pair of electrons right on top. So if you take away that lone pair, just look at what is left in the bonding, the bonds, we've got a trigonal pyramid molecular shape. Okay, next one, CH4. Typically, we use black spheres to represent hydrogen. So I'm going to pull apart the NF3, and I'm going to insert the connectors into the carbon. And referring back to the Lewis structure for CH4, it is tetrahedral geometry and tetrahedral molecular shape. Now take a look at this build. So here we've got a perfect tetrahedron. Each of the bond angles, since they're all the same carbon-hydrogen bond, are the same distance apart in space, 109.5 degrees. So you can see how this is kind of a fun one to play with. If you set it down on a flat surface, the carbon's raised up a bit, and there's another C to H bond pointing straight upwards. This is the tetrahedron, if you can imagine the vertices of all of these molecules. It would form a triangular base pyramid or a tetrahedron. Okay, NH3 is molecule number, another one of our molecules. NH3 is going to look almost identical to the NF3. The only difference is, instead of the previous one where we had orange balls, now we have the white balls representing hydrogen for the satellite atoms. And again, if you put it on a flat surface, the nitrogen atom is up a little bit above the hydrogens in the plane. Interestingly, if you were to take a build, and we'll see this in the next one, CF4 is the next one. Remember the trigonal pyramidal shape here. And if we take a central carbon and build CF4, you'll see some similarities. I'm pulling off the hydrogens and putting on the orange balls, which represent halogens. Okay, so here's CF4. And again, just like CH4, we've got a perfect tetrahedron. All the bonds are the same, C to F bonds this time, and they're all 109.5 degrees apart. Now, here's the part I wanted to show you. Let's say I just yanked the top bond off. All of a sudden, we have a molecule that looks an awful lot like the central nitrogen, the NH3 or NF3. Isn't that funny? Because that's where the lone pair of electrons belongs in the nitrogen molecule, the ones that have nitrogen as the central atom. Okay, moving along. Number 7, CH2I2. CH2I2. Now this time, it's roughly the same. We're talking variations on a theme here. But now I've got the H's are represented by the white balls, and the iodines or any halogen we're using orange to represent. But you've got 4 bonds. They form a tetrahedron, bond angles of almost 109.5 degrees exactly. The only difference between this molecule and CF4 or CH4 is that because fluorine, or rather iodine here, is more electronegative than the carbon, electrons are drawn towards the halogen side of the molecule, the iodine side of it. So this is actually not a nonpolar molecule, whereas CH4 was nonpolar and CF4 was nonpolar. This is a nonpolar, a polar molecule, because electrons are drawn to one side more strongly than the side with the hydrogens, and that's due to electronegativity trends. Okay, so that's CH2I2. Number 8, this is a fun one, PF5. Now, PF5, this time we're going to use a different colored ball for the central atom. We're going to use a light colored pink. And if it's PF5, that means it's all halogens. So 5 fluorines connected to this central phosphorus. Sometimes it takes a while just to get the connections all put together. But this one, if you look at the Lewis structure, our electron geometry is trigonal bipyramidal. Okay, so this is not a tetrahedron. If you set it down, it doesn't quite know what to do, doesn't quite balance. If you rotate it on one of the bonds, it looks like this. So it's got a different shape. There are 1, 2, 3, 4, 5 electron groups around the central atom. And the reason they call it trigonal bipyramidal is if you envision like the plane where the 3 bonds are all together in the same plane, and then have the vertices of each of those point either down below that plane or up to the bond above it. It's as if you had 2 triangles with 2 triangular base pyramids facing bottom to bottom. So hence trigonal based, bipyramid meaning 2 pyramids. The bond angles here are interesting. They're 120 degrees apart within the plane of the bonds, or if you consider the bond angle distance between a bond within the plane to the bond either above or the bond below the plane, that's a 90-degree angular separation. So there's 2 different angles to remember for this electron geometry. And you always want to put the more repulsive bond, or actually lone pairs are slightly more repulsive than bonding pairs of electrons. So if there is a lone pair, you place it in the space either above the plane or below the plane, so as to get it away from the other bonds slightly more. Okay, number 9, SF6. So this one, we're going to use a yellow ball. And this time, our geometry is octahedral. So the last two, so SF6 and PF5 were the molecules that violate the octet rule by having more than 4 bonds around the central atom. Okay, so here's an octahedral geometry. Octahedral. And this time it's as if you had two square-based pyramids within the plane of these bonds, and then pointing either above or below the plane of those bonds. Every single angle in this electron geometry is 90 degrees, no matter how you tilt it, and whether you consider the bonds within the plane or the bonds above or below the plane. Okay, so that's SF6. Molecule number 10. This is a really fun one. It's O2. Okay, so we're just going to take 2 red balls, and now we're going to use these longer connectors, which are more flexible than the shorter connectors. And we're going to connect the 2 red balls, not just once, not just once, but twice. And in the Lewis structure, we have a double bond. In our modeling kit, we get to indicate a double bond thus. Now notice that the 2 bonds that make up a double bond are in the same plane, and that actually is reflective of the reality of a double bond. You can't twist a double bond. It's locked into place. Whereas a single bond, you can actually rotate it. There's what they call torsional strain, and that affects how the molecule behaves in 3-dimensional space. So O2 with the double bond is locked into place. Molecule number 11 is N2, another super interesting one. This time we're going to use the 2, I've got 2 light blue colored balls. And in the Lewis structure, if you remember, there was a triple bond between the 2 nitrogen atoms. So this one requires quite a bit of pushing in, but we got it. So we've got a triple bond between 2 nitrogen atoms. And this one's really rigid. You can't bend this at all. The 2 atoms of nitrogen are locked in place, not just with 2 bonds, but in 3 bonds. So there's absolutely no ability for these atoms to move around. They're super locked into place, which reflects the reality of a triple bond. It's a very rigid bond. Okay, last one, CO2. Now our Lewis structure for CO2 had a central carbon that was double bonded to each of 2 oxygen atoms. So let's see if we can build this. So we're going to see 2 double bonds. And this is not only cool to build, but cool to think about. Okay, here is CO2, the double bonds, 1 to either side, and the bonds within a given double bond are in a plane. So this double bond, they're in a plane. This double bond, the 2 bonds within it are in a plane. Now, the orientation of those planes are perpendicular to each other, which is actually really interesting because it tells something about how carbons, the holes that are drilled into this plastic ball, are reflective of the bond angles in a real carbon atom. And not only is this rigid, but the way the electrons are shared, the second bond of a double, and this is getting into organic chem a little bit, but it's called a pi bond, and the electrons float actually above and below the plane of a straight line drawn between the central atom and the satellite atom. So like in this double bond, one of the two bonds has a sharing of electrons right in between the atoms. The second bond actually has electrons floating above and below that line, which was like really interesting, because pi bond, they call those pi bonds. You can actually one interesting material is called graphite. It's the stuff in pencils, and it's nothing but carbon. But graphite conducts electricity because it consists of lots and lots of pi bonds. So you can actually have electric current flowing through a covalently bonded compound like graphite, which is insane. So some of these peculiarities only come out in when you get to play with an actual modeling kit. So unfortunately, you didn't get to do that today, but I invite you to borrow one and just play around with it if you have a chance. Or there are some really good 3D computer animations as well. Thanks for your good work.